Hi, my name is Rezvan Farahibozorg. Welcome to this practical video on Probabilistic Functional Modes or PFMs. PFMs, as we learned in the lectures, are a new FSL tool for estimating resting state networks from functional MRI data, and the key characteristic of the model is that it does so for population and individuals simultaneously. The practicals are written in Python, and we will use Jupyter Notebook to go through the exercises. However, if you are not familiar with Python, it is not a problem as the instructions should guide you step by step through the different exercises. First, let's go to the PFM directory and then download the Jupyter Notebook that includes the exercises and the instructions. And finally, we will use FSL Python to load the Jupyter Notebook. This is included here, which we can open, and the rest of the practical will happen there. Before you start the practical, we strongly recommend that you go to the Human Connectome Project website and sign up, because the data that we have used here is from HCP and they require sign-ups for usage. The first part of the practical includes some general introduction and references for PFMs, what they are, how they are similar and different to IC and dual regression for estimation of the resting state networks, as well as the characteristics of the modes, especially the spatial topographies of the modes across the brain voxels, the spatial maps, and the temporal connectivity or functional connectivity between the modes, which we refer to as temporal netmaps. So these are two of the key characteristics that we will focus on throughout the practical. The practical has two main aims. The first aim is to look at the group level PFMs and compare them to group level ICA RSNs, and the second goal is to look at subject-specific PFMs and compare them to dual regression networks. Throughout the practical, you will see some boxes that look like this. These are Jupyter Notebook cells, and when you see hashtag executable cell at the beginning of a cell, it means that you can press the run button at the top and run that cell. When you run a cell, you first see a star in this bracket, and once it has finished running, it will be replaced with a number. Let's just run this one, which will print a figure, a flowchart of the Perfumer framework, and then move on to the instructions for the practical. The first bit includes some general summary of the pre-processing steps that have been performed on the data before we fed them into the PFM modeling. Then there is instructions on how to run the model, and because this one takes too long for this practical, we have already run the model, and this is just for illustration of how it can be done. We will see more instructions on how to run the model in a bonus section at the end of the practical. It will use a software called Perfumer, and it will receive a bunch of input arguments to specify the input locations, the number of modes, and the output locations that we want to save out our data. After we run the model, then the main focus in the practical will be to do the post-processings and see how the results look like and how to interpret them. The first part, the first executable cell, it just includes importing a set of libraries from Python, as well as a Python package called Perfumer, which is specifically useful for our purpose, as well as loading a set of useful variables such as subject names, session names, number of modes, which will be 50 throughout this practical. So let's just run this one. And we can see that the number is here, so it means that it has finished running. Okay, So the first set of the results are group level results, starting with the spatial characteristics of the modes, so the spatial maps at the group level for PFMs. These are the group average spatial topographies of the PFMs across the brain voxels. This cell loads the PFM spatial maps and saves them as nifty images. So we can just run it, and it is running. There is a star here. We wait until it's finished. And once it's finished, we move on to next stage. We have saved the nifty files, so we can use Fossilize to load them and visualize them. This command here, which you need to copy and paste in a terminal to run. I will not do this, so you can just load and paste it here, and then it will do this in open this in the Fossilize. You can overlay PFMs and ICA modes and investigate how similar or different they are. Throughout the practical, you will also see some cells that are marked with questions. These refer to some small questions that you will be asked to answer to. For example, if you run this, you will see a question. When you answer to it, you will see if your answer was correct or incorrect before moving on to the next. The next subsection 1.3 now focuses on the relationship, a spatial relationship between the spatial maps of the PFMs. In the previous section, we looked at how the spatial topographies of the modes individually are, and here we will focus on how they are spatially related to each other. In other words, how much they are spatially overlapping with each other. So far, we have focused on PFM results. Subsection 1.4 then focuses on doing the same steps now for melodic ICA components, with the aim that we want to then compare these to PFM components. So first, just loading them ICA as spatial maps and saving them as nifty images, and then running quantitative comparison with the spatial maps that we get from the PFM. So this will be done during subsection 1.5. So far, we have focused on spatial characteristics of the RSNs. This section focuses on group level temporal characteristics, especially focusing on temporal correlation matrices or temporal net mats. And these are the group average correlations, temporal correlations between the time courses of the PFMs. When you run this cell, you will see the temporal correlation matrices for the PFMs and for ICA dual regression netmats, and you can see that there are qualitative differences between them. I encourage you to think about these and try and interpret why they are different, and discuss this with your tutors as well. This subsection concludes our investigations into the group average PFM results and their comparison to ICA. Next, we will move on to subject-specific or individual-specific results, specifically focusing on the spatial maps, time courses, and temporal netmats. Because fMRI data at single subject level can be quite noisy, estimation of the spatial maps at subject level is also quite challenging. Because of this, Profumo uses a double Gaussian mixture modeling to separate the signal from background noise. And here we load these signal-specific spatial maps and noise-specific spatial maps, and we save them as nifty files. You can now use Fossilize to load the subject-specific spatial maps for signal and noise elements and see how similar and how different they are. So let's do that together. if we look at them side by side and have a signal component on the left a noise component on the right, you can see that, for example, here in the case of a motor network, the signal component and the background noise have been separated quite well, so that the noise is not sneaking into the signal element. Here is another example of another motor network, and we can see the same scenario. So you can go through all different components and see in what scenarios the model is doing a good job at separating signal from background noise, and in what cases it is not doing a very well job. We can make the same kind of comparison now between Profumo spatial maps and ICA spatial maps. So you can use fossilize again going to the terminal and running this line to see how the dual regression and PFM subject specific spatial maps are similar and different to each other. The next subsection 2.3 focuses now on the time courses. We focus on on an example network, the default mode network, and an example subject, and we visualize the time courses again for the signal and noise elements. Have a look at the time course and the power spectra that the model gives you, and compare it for the signal and the noise components, and see how it links to the previous things that you learned in dual regression and FSLNet practicals. Finally, the last part of the practical focuses on subject-specific functional connectivity or temporal net maths, and here we have 4 subjects. We load and visualize the net maths, the functional connectivity for all of these subjects. Have a look at how they are similar or different to each other, and you can notice that there is a lot of variability between the subjects. Think about why this is happening, and if you were in doubt, you can discuss this with your tutors. The final bonus section of the practical is just the documentation of how to use PFMs and all the input arguments that you can provide to the model, and the description of what each of these arguments mean. And at the very end, you will see 3 main arguments: the data locations, the number of modes, and the output directory, which are mandatory. So if you specify these in addition to any of the optional variables, you can run the model on your own fMRI data and estimate the RSNs. And with this, we can wrap up this practical video. We hope you enjoyed going through these exercises, and if you are attending FSL course, we encourage you to discuss all of these with the other attendees and with the tutors to make the experience more useful and enjoyable for everybody. Good luck!